Okay, we've got another lecture going today, and today we're going to talk about concurrent force systems. But most importantly, these concurrent force systems are two-dimensional. This is the type of concept that you'll be using quite often in your engineering career, and I want you to get a good handle on it. So we'll take our time on this and take as many lectures or as much time as we need. My goal on all these is to help everyone, whether you're young engineering students or graduate engineers that are studying for maybe professional registration, and you have to go back and take an exam that you haven't had statics or strength materials or engineering mechanics in a while. And that's why these are really important to follow these lectures. I've found that over the years, the best way that I have communicated this information and really got my point across to the students and the young engineers is, we kind of sit at a table with a question, and I usually take a blank piece of paper and just start lecturing and doodling and working examples and doing whatever we need to do. And if I'm working on a beam, I'll just do something like this, and I'll say, okay, we got a beam like this, and then we're going to put a load on it, and then we're going to draw a shear moment diagram, things like that. And I just kind of just scribble as I go along. And what I found out is almost every time that I've done that, the person sitting with me says, Mr. Boltavsky or Professor Ted or whoever I am to that person, they ask me if I can have the piece of scrap paper that I was kind of scribbling on because they want to use it. So I realized that maybe all the years of the examples and the notes had a lot of value, and as I'm getting up in my career here, I thought that right now the important part is being able to pass this on. So I don't know how many lectures this is going to be, and probably going to turn out to be hundreds and hundreds because I have a lot of information. I'm going to talk a little bit about real world examples on some of these things where where over the years I've seen structural failures or mechanical issues that come into play, and I want to make certain that all of you have a chance to ask me questions. I'm sure we're going to be able to have comments on this, and I'll come back and answer those questions. I'll have lectures where I do nothing but talk about past examples of things, have some really good examples of how all this works. So I want to talk today. We talked last time a little bit about mass and force, what was the difference between them, and now we're going to talk about the fact that force, whether it's gravity or magnetic, whatever, it has effects on a body. It can change the direction or the way something's moving. It can also deform the body. Now, when we're talking about statics, especially, we're talking about kind of this external load on a body and what might be happening internally a little bit, but that's more when we get involved in strength of materials. Although we will talk about some internal forces during lectures that have to do with statics. So the resultant of a system is important because it's the simplest equivalent system of a set of forces or loads. So let's talk a little bit about the characteristics of a force. So we're going to look at this stuff here. We're going to say that we have a direction, so that direction is going to be either newtons or kilonewtons. Now I will tell you that I live in Cleveland, Ohio, in the United States, and I have not had over the years many jobs that we had. Everything was in U.S. units, so pounds, kips versus newtons and kilonewtons. But we're going to talk about all of that. But remember that a pound is 1,000 pounds is equal to 1 kip. So when you see 1 kip, that's equal to 1,000 pounds, and we'll be talking about that as we go through all these. We also have to have a direction, so that gives us a slope in a sense. In this case, in this example, the slope is it's rising 6 units as it's moving to the right 5. And then we also have to have a point of application. So that's a contact, usually between two bodies. So we have a we have to know that a minus sign changes the direction. So in this example here, if this force changed and this F here became a negative F, then it would be the same exact load, it's just it would be going in the opposite direction. It's because we're going to be summing things vectorially. We also have a direction, theta. In this case, theta is counterclockwise from the positive x-axis. Now listen, everybody, when you're working on these problems, whether you're in school or you're on the job, you've got to put your units down always, and you have to make sure that your positive and negative signs are correct, and you have to take your time and really be very organized. I see a lot of work that comes in, both professional work as well as academic work, that is just, it's just not good. It's jumbled and it's not clear. Take your time and make sure that you place things easy to understand. Like this example right here. Here's a force F that is shown in the XYZ plane. So you have an X component of 7 inches, a Y component of 5 inches, and a Z component of 4 inches. You have 3 directional angles, theta X, theta Y, and theta Z. So you can look at that and you can understand what that means. But if that was not clearly written, that could be a real problem and a real mess. So take it from me, when you get on the job and you're working on problems and you're working on for clients, they have to be able to have a clear understanding of things. And your work product, especially if you're doing any kind of sketches before you even put it to AutoCAD or Revit or any of the programs that are out there, has to be clear and easy to understand. So here's an example of a load. This could be anything. This block could be a piece of equipment that's being pulled up onto a roof. It could be a counterweight on something that's going on in a material handling location. But it has a magnitude. It's 1,000 pounds. That load is 1,000 pounds. Right here. Let me get this right for you. This is 1,000 pounds right there. Okay, and it's at an angle, theta, counterclockwise from the horizontal. And the point of application is through P. So those are all the things that we talked about that had to be satisfied. Now if it's a scalar, it's only a magnitude. So in other words, a scalar is 1,000 pounds. The load's 1,000 pounds. That's it. That's a scalar value. But if it's a vector, it has a magnitude and a direction. Okay, so it's 1,000 pounds to the right, or 1,000 pounds at 40 degrees counterclockwise from the positive x-axis. That's a vector. So a lot of times you'll see vectors like vector A with an arrow over it, like you see here, or bold, very, very bold, bolded up, so that they can be very much denoted from a scalar. Talk a little bit about transmissibility when you have a rigid body. Like here's an example of a stalled car. You can push on it from left to right here with a load P, or you can pull with that same load P, and it's going to do the same thing. Hopefully it's going to move that stalled car to the right. So the motion of the car is the same, but you could possibly have a little bit of an internal effect there. You could have a point where you're going to maybe deform the bumper or rip something off the car. That would be something that would be involved with stress, and that would be when we're talking about strength of materials. You're going to get into classifying loads, and as I tell all of my students, being a good engineer, being an effective engineer, means that you can go out in the field and you can understand how loads are being applied to a structure or a piece of equipment. You can look at it and you can determine how that load is affecting. So in this one here is a simply supported beam, and it has a concentrated load P near the center, not in the center, but it's right in the middle. Maybe that's a beam and there's an HVAC unit on a roof that's being applied to it. Or you can have a distributed load like this over here, where you're taking the load and you are uniformly, in this case, distributing it across maybe it's a roof slab, maybe it's a snow load or some sort of fluid load. So this is important to be able to understand it, because once you apply the loads to a structure, then I'm going to teach you techniques to be able to determine what kind of stresses and loads are being applied throughout the structure. We're going to learn about something called a free body diagram, which is taking the body and separating it from everything else except the loads that are being applied to it. So in that case, what you have here is, I'm showing you an example of a plate with a cable. Now, the reason I bring this one up is this was actually one of my very first jobs that I had years ago. I'm talking about 1982, where we had a large slab like this. Okay, it was all big concrete slab. It was thick. It was like 30 foot by 30 foot. Like this was 30 by 30. It was like a foot thick. And we were putting it in an intersection. So we had, we had 4 streets coming together in downtown Cleveland. We had a big excavation right in the middle, right by the baseball park. And we had to come in at 2 o'clock at night and lift this big load off a truck and have it set right in the intersection, and then have it plated and covered back before the next morning to allow rush hour traffic. So what I had to determine was what was the best place to set. We weren't grabbing it from the corners, and there were some holes in it and so forth because it was a manhole cover, and we had to find the spot to put the lifting lugs so that this thing could be grabbed by a crane and lifted and have it come off somewhat level, so when it was brought over and set down, it didn't crack or didn't have a problem. So this was an example right out of college of taking something as simple as a resultant of a concurrent force system and using it to actually get the job done. And the reason this is concurrent is that there's going to be loads in these cables, and they're all going through the same point. So that was the stipulation, right? They were multiple loads all going through the same point. We're going to pick up next time on the resultant of 2 concurrent forces, and we're going to start looking at methods, graphical methods, in order to solve for a 2-dimensional resultant of a system of concurrent forces. So I'm always going to give you some lecture and explain some derivation behind things, and then from there we're always going to do a lot of examples, because we're engineers. We like examples. We like to solve things, and we like to come through and do the calcs and see how they're working and how it actually comes to fruition at the end. So take a look at this video again a couple times, and next time we get together here, I'm going to talk a little bit about solving for these concurrent forces. So hopefully everybody's doing well.